Okay. Oh, that's, sorry, I have to, there we go. I have to tell it which screen I want to mirror or to record. It's recording, microphone is on. Where's the microphone? Look at that. Isn't that great? I'm super happy about this. I used to have a tether. Now I can walk around. Okay, put it that way so you can see the little light. Okay, so let's take a look at these. I'm going to move this one down because it's too much. We're going to need some room. There we go. Okay, so the whole idea, which hopefully you got from the reading, but if you didn't, we're going to redo it, is that we're looking for, so we're going to be going through this series of problems. Why is this not? Okay, there. Series of problems. So, we did the preliminaries, and we're going to have to deal with those preliminaries for each problem, uh, but we're going to go through a series of problems. The first problem is, how do we find the root of an equation? So nice and simple. How do we figure out where a particular function crosses the x-axis? That's what a root is. So this is the sort of thing you did in algebra class. So you can think of this course as mirroring some of what you've learned in various math courses. You started off in algebra. How do we figure out the solution to a linear equation? Nice, easy equation. We can't, this one is a harder function to find the root of. Roots, remember, is just where does this equal 0? That's it. Okay, so the idea behind the bisection method, I'll just do this real quick, and then we will, which I should have done on a video, but we didn't, so there it is you have a function. Here is the function. Good enough. And you don't know where it crosses the x-axis. Of course, you have this graph here. Isn't that nice? Right there. There it is. Well, yeah. If I have a graph, you can just tell. But you don't have a graph. Pretend that you're just trying to get a computer program to figure out where this thing crosses the x-axis. So you're going to give it some inputs. You're going to say, okay, we're going to start with this point. That point we're going to call A. And over here, we're going to pick another point. That point we're going to call B. Whoops, I wanted to use blue. So I know you've probably already figured this out, but I just want to make sure that we're all on the same page. So the important thing about A and B and your function are the following three properties. Two properties. Yeah, I think it's just two. We need the function to be continuous. It's essential. If your function is not continuous, then you could start out down here and just pop up there like I don't know, a warp, whatever, a wormhole or something. Just pop up and not cross the x-axis. So it's got to be continuous function. And then the other thing, the function value for A and the function value for B have to have different signs. That's it. As long as you have this, then we can for sure find where there is. So the way you do this is you check to see that A and B have different signs. So here f of A is less than 0, f of B is greater than 0. So we're good. Yeah, f of B, that's up here, f of A is down here. And so then you split the difference, call it the midpoint. Called the bisection method, midpoint. And then you ask yourself, which way does the midpoint go? So the midpoint is up here somewhere. And so you say, oh, that's greater than 0. So we get rid of B and we change the name of M to B. And then repeat. Keep going. So we're going to do this over and over again. Here's the midpoint. Oh, look, that's greater than 0. So get rid of the B and call this B. Now the midpoint is right here. And notice that the function value at the midpoint is less than 0. So now we get rid of A and we change the name of M to A. So you can see how eventually we're sandwiching, we're coming closer and closer, squeezing together. Eventually we're going to get here or there, the there that we're looking for. So we're going to do this with this particular function. So the nuts and bolts are that you make a nice table. Of course, we're going to want to do this in Python eventually, but for now, let's do it with a calculator. So you've probably already done this, but just in case, let's see, we'll call this, let's see, we'll do this way. I think that the book had 6 columns. So you had A, B, no, M, sorry, M, B, and then F of A, F of M, and F of B. So we have 0, 1/2, and 1 as our first bisection. And they want us to do, what is it, 2 or 3 bisections? Whatever it is, we'll do maybe 4. We could do 4. It's not hard. Now that you sort of see, it's like super easy. I forgot to do this earlier. I'm going to do it right now. Whoops, what just happened? RAM cleared, it says. What does that even mean? Oh, it means that I have a fresh, clean slate, apparently. Okay, so I'm going to type in this function into my graphing window. And the reason is that if you have a graphing calculator, that's probably the easiest way to get it to compute. I'll show you this once I get done. Okay, so here's that. Let's see, can I get my camera? Where's my camera? There it is. It's going to be black for just a sec. There we go. There, see? There it is. So then once you have that, you can easily compute values by, where is it? Second, variables. Oh, no, it's just variables. Vars, yvars function. We just have to basically do this once, and we can just press entry. So there it is. Oh, whoops. I didn't intend to do that. Maybe I should do this without hovering. Let's see, quit. And then vars, yvars function. There it is. Okay, y1 of 0, for example, is equal to -1. So that's negative. I'm going to do the rest of them. Whoops, here. So less than 0. That's what, if you were looking at those tables wondering what all those symbols meant, it's just a less than 0. Myself, I have trouble looking at like the less than 3 and understanding that less than 3 means like heart. Isn't that right? In some countries, I don't know. Okay, so let's do y1. So now that I've got this, we can do y1 of 0.5. And I got -0.17, but what matters is that it's less than 0. Oh, I don't like less than 0 for my little table. I'll show you what I prefer, but I wanted to match the book for this one. And then we'll do entry and change this to 1. And that is positive, so greater than 0. So I much prefer, when I do this, to just say that's going to be negative, negative, positive. That's much easier for me. So here's how we would repeat this, is now the new A is the old M. The new B is the old B. So you notice that you're going to take the gap. So what I mean by that is you compare like these two, those are both negative. Whereas, different color. These two, one of them's negative, one of them's positive. You want that. You want negative, positive, so that you're always sandwiching that root. All right, let's go ahead and bisect again, 3/4. And we already know that this is negative and this is positive. So the only thing I have to figure out is 0.75. And I got positive. So let me just do one more step and then see if you have questions about the way this works. So 3/4. Whoops, that's not where I wanted that. 3/4 takes the place of 1. So maybe one way we could do this is this one's always positive, this one's always negative for this problem, only for this problem. And then this one is 1/2. So split the difference between those two. Things are getting a little bit funky. We're going to have to do 5/8. 5/8.625, is that right? So 0.625. So yeah, it's just because you take whatever the first one is. If the first interval has negative for A, positive for B, then that's the way it's going to be all the way down. If the first interval has positive for A, negative for B, it just means that the function is going the other direction, and you would keep that constant, or consistent. Okay, what is up with this? Oh yeah, we already know that this is negative, this is positive, so we just have to work on the midpoint. So let's do that, and then I won't do any more because this is getting boring, and I want to see if there are questions. So that gave me a negative number. So a negative number, which means that the very next level will be here. So 5/8 and 3/4, so that I can consistently be negative then positive. So we can do the split the difference there. It's going to be 16ths though, 11/16. I don't want to do it. I refuse. Okay, so what sorts of questions do you have about the procedure? Do you think you can do it? You're okay with that? Or is there questions about how this works? Or anything else from the reading that you didn't understand because it was confusing and they kept referring to Taylor polynomials? So let's take a look at this next one. I don't know, did I just say to do A or did I say A and B? Oh, good, good, A and B. Yeah, B was a little annoying. But if you have your calculator and you can sort of punch the function in, which I'm going to do right now, it's not as bad. Now, one thing to note, what's annoying about this for me is that we know what the answer is. But that's not, it's both annoying and helpful if you think about it, because you know what the answer should be. In the case of the first problem, the first part A, I don't know what. I mean, I'm sure that Desmos knows, but I don't know. Give me a sec. 1/2, and then times x minus 1. So this function has 3 roots, obviously. X equals -1, x equals +1/2, and x equals +1. So you already know what the answers are. But once again, this is because, it's just, so that's kind of helpful because you know that it has answers. But let's see what happens, just a minute, when we try punching this in. Give me a sec. I need to make my table. This table is going to be a little bigger because of the numbers. Okay, so we've got A, M, B, f of A, f of M, f of B. So we have -1.25, 2.5, and we should check. So remember, the rules are that this thing has to be continuous, which it's a polynomial, it is continuous. And these two function values have to be different signs. If they aren't, no sense in going any further. So let me just double check those, and then we can see where this ends up being. 1.25 is negative, and hold on a minute, 2.5. 3 is positive. So we've got a negative and a positive, so we're going to get the split the difference. And here, I probably could figure it out, but I don't want to. So 2.0, yeah, it's going to be 3/8, isn't it? Let me do this, though. So I'm adding these two numbers together, add 2.5 plus -1.25, and then I divide that by 2. I'm sorry, 5/8. Yeah, good thing I didn't just spout it off. Okay, so 0.625. My handwriting is horrible today. We'll do that. Come on, buddy. Why is it not erasing? Oh, I see. Okay. Okay, so there's my, there. That's a little bit better. So let's see what f of m is. Let's see, this is 0.625, and I get negative. And so that means that 0.625 and 2.5 will be the two endpoints for my next interval. Now it should be clear, like before. I guess what's kind of interesting about this is that before I did that, you actually had 3 different roots in your interval. I think that's kind of interesting. Like look at the interval. The interval goes from -1.25 to +2.5. All 3 of those roots, we know where the roots are. -1, +1/2, +1. They're all in that interval. But we can continue. So even if you have multiple roots in your interval, you just keep going, and eventually you'll narrow it down to one of them. So the next step, we'll just do one more step, but we're going to want to talk about speed, accuracy. Sorry, I just realized. Matthew? So that's 3 missing. Wait a minute. 3, 6, 8. Do we have 11 in here? Are all of you in this class? I thought I only had 10. Okay, I'll see you later. Well, no, you have the games. We got to keep you. All right. Yeah, you gotta be here for game time between classes. All right. Well, let's get one more iteration. Then we need to talk about this whole what's going on. So let's see, 2.5 plus 0.625. That's what I'm doing on my calculator, and then I divide that by 2. So that gives me the midpoint. Just the average of those two numbers is 1.5625. We already know this will be negative. That'll be positive. So all that's left is to do the function value. Okay. And it's positive, and so the next level will look like this, but I'm not going to do the midpoint because this is becoming painful. But presumably, if you understood what was going on, you could have done this. Eventually, you'll get closer. Both of these things will get closer to 1, because that's the only root that's between them at this point. All right, are there questions before we talk about how long this is going to take? So, any issues? It's tedious, but that's why we have computers. So how long would it take, I guess, is the question. That's one of the things that you'll be answering on your homework for tonight. But that's what I'd like to know. You know, it seems pretty slow here. You've got a huge gap there between 0.625 and 1.5625. Even if we didn't know what the root was, that's a huge gap to have to contend with. Like, it's somewhere in there. So how long is this going to take? Well, let's say that I'm interested in getting to within, let's say, 10 to the negative third. That's how close I want to be. In other words, whatever answer I end up with, whatever midpoint after the very final, so basically you keep doing this, and the final midpoint, that's your answer. Like up here, I guess my final midpoint would be 11/16. So 11/16. How close is 11/16 to the answer? Well, this one's actually kind of easy because each time you split this, like you can, here's how you could look at this. In this first splitting, you are within 1/2. So how close? I'll put that up here. Close, question mark. How close are you? So in this first splitting, the root, the thing you're targeting, is somewhere between 0, somewhere between 0 and 1. And you split the difference. You took the middle. So what's the worst case scenario? What's the furthest away you could be in that first thing? You could be 1 away. Well, your guess is 1/2. Could the root be 1 away from 1/2? Yeah, it's 1/2. Yeah, I know what you're thinking. That's the length of the interval. But your guess isn't 0. It's not 1. Your guess is you think the answer is 1/2. So how close are you? Yeah, you're within 1/2. Okay, so how close are you? You're within 1/2. 1/2. And then the next one, how close would this be to the truth? 1/4, yeah. So now you probably see a pattern. The next one, doing the same thing, is going to be 1/8. And then this one is within 1/16. So each time you do the bisection method, you split the distance between your guess and the truth. Now, this should be somewhat familiar. Let me write it down for you, though, is we are interested in this sort of thing. P sub n is your nth guess, and P is the truth. And so here's the deal, is that this P sub n is a sequence that goes to P. I know, we're going to get to this. We're doing a order of convergence here. And so we want to know the limit as n approaches, wait, how did we do this? We have n approaches, and we don't have a limit, do we? Infinity? Yeah, we do have a limit, sorry. We have P minus P sub n, or is it, it doesn't matter, it's absolute value, plus 1 over, I think it was Pn plus 1 minus P, wasn't it? Yeah. Let me get rid of this. Sorry. Pn plus 1 minus P over Pn minus P to the alpha. And we want this to equal a finite number. Okay, well, we'll notice what's going on here. I think we can figure out what alpha is pretty easily. Let's go back up here. So the number, the how close, that is worst case scenario of this. So that's how close you are. And then the one below how close, so if we're, let's say we're on the one that has 1/8, this is the denominator, this is the numerator. So, so anyway, if we let alpha equal 1, then this fraction will always be, is it 2? Is that what I'm getting? Let me see. Or 1/2. Let me see, 1/8. Yeah, it's 1/2. So just as an example, this is just one of, I mean, this is going to be a consistent, the next one is going to be 1/32nd, the next one 1/64th, and so on and so forth. So, so this thing, if we just take one of the examples, the 1/16th over 1/8 to the alpha, and I want this to be a constant, this 1/16th, whatever number's up there, is always going to be 1/2 of this. And so 1/2 of this divided by this is, I guess it's 1/2, right? So if alpha equals 1, then that will give me a limit equals 1/2. If alpha is bigger than 1, then this thing will grow too quickly and you'll have a limit of 0. If alpha is less than 1, and we don't, I mean, without having to show you all of the calculus, if alpha is less than 1, then what happens is that this thing, as you increase this, this will be 1/32nd over 1/16th, 1/64th over 1/32nd, and so on. If alpha is, wait, what is it? If it's bigger than 1, you'll go to 0. If it's less than 1, you'll go to infinity. Guaranteed. So if you really want, we can demonstrate this, but it has to do with the fact that we know our calculus. We know how to compute limits of sequences. And so, yeah, without actually, well, here's what happens here. I'll even, yeah, I probably should have done this way anyway. This is the limit as n approaches infinity of 1/2 Pn plus 1, because no matter what bisection method you're using, you're doing this. Oh, Pn, sorry. And so that's going to be 1/2 times Pn minus P to the 1 minus alpha. And so if alpha doesn't equal 1, then this thing will either go to 0 or it'll go to infinity. Because if that alpha is bigger than 1, this goes to infinity, or 0. If alpha is less than 1, this will go to infinity. So, so anyway, that's the deal there. So this thing has an order of convergence of 1, first order convergence. And then we can talk about the big O. So the big O of this, so this converges, this one is big O of 1 over 2 to the n. Mainly because this is exactly 1 over 2 to the n. Look at my sequence. And if you have, let's say you have different starting points, then you would have different numbers here, but they would still be half each time. Half, 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 half. And so that's the big O. It's 1 over 2 to the n. So it's got that convergence. That's how fast it will converge. It converges like that fraction, which is pretty good. I mean, 2 to the, let me show you a couple of numbers here. 2 to the 10th. Did we do this before? Oh, I think we did. There was this on one of the homeworks. 2 to the 10th is approximately 1,000. I know it's not exactly, it's a little over 1,000, but this gives us a way to estimate how quickly we're going to get to the answer. So 2 to the 10th, you get 3 digits after 10 iterations. So 10 iterations will give us 3 digits closer to the truth. Another 10 iterations gives us another 3 digits. So every digit is going to cost us roughly 3 iterations. So if we want another digit using the bisection method, do 3 iterations. A little bit more. Technically 10 iterations to get 3 digits. But so that's why we're interested in speed. We want to be able to predict how quickly will we get to the answer. Okay, so that wasn't too long. Let's take a look at the book so that you know what to do for next time. So I thought, I didn't want to overwhelm you with something new, but I should say this. Here, we can do some experimentation, is that this is what we're doing, at least for this whole chapter, and then we'll have a test after this chapter. Is we'll have some fun stuff that we can do instead of just whatever we did past week. Order of convergence, that was painful, wasn't it? So just so you know, what we're doing is we're trying to solve this equation. You have a function, set it equal to 0, tell me what the solution is. That's it. That's it. So there's various ways to do this. One of them is, of course, the bisection method. The one that we're going to learn on Monday, I'll give you a quick preview. It's called the fixed point method. And it's a little bit more specialized, but it allows us to solve equations like this. So if you have an equation like that, you can solve that using the fixed point method. And I will even solve this for you right now, super quickly. The way you solve this using the fixed point method, we'll go over this more on Monday, is you change the equation to be like that. And then, let me just do this really quick. Let's clear everything out. Okay, yeah, this is really cool. So that's why I thought this will be worth it. Then we'll go back to bisection. We're going to talk about homework. But here's the super cool thing so we have cosine of x equals x. So here's how you solve it. You just take a guess. I think 1 is the answer. Is 1 the answer? I'm pretty sure it's not, but let's find out. So the way you would find out is you would say, what is the cosine of 1? So we'll do that here. Sorry, I have to look over my iPad. Okay, there it is. So cosine of 1, what is the cosine of 1? Oh, I was wrong. But now that gives us our next guess. And we'll say, what is the cosine of that number? 0.8, see? And then we'll do the cosine of that number. I'm just hitting enter. Most calculators do this, is if you have a formula, it'll just repeat the formula every time you hit enter. And that's the cosine of 0.857. And then this is the cosine of 0.65. Notice that the numbers are getting closer and closer to something. If I keep hitting enter, that's the solution. Well, eventually. It looks like it's pretty settled down there. But so the actual solution to cosine of x minus x equals 0 is, well, approximately 0.739085133. 2 maybe? Oh, interesting. Oh, because of round off error. This thing is cycling, isn't it? Wait, let's see. Is it cycling? That's always fun. 332. Oh no, it stopped cycling. I thought it was cycling up above. Okay, I guess we've settled down. It looked like, let me find the list. I've got it. I put it online just before class. Oh no, reconnection successful. Okay, sorry. It's my video recording software just reconnected. Okay, let me grab the homework just so I know what I'm talking about. Here we go. Problem 6, 7, 8, 9. Wow, 6 through 9, and then 15 and 16. Okay, so 6 through 9 are all just doing the bisection method again. And I am okay with you using your calculator. I am okay with you using a computer. we'll do this on Python at some point. I don't know if we'll do it on Monday or Wednesday next week, but it's so easy to implement the bisection method. I mean, you could tell the AI to do it, but it's like 3 lines, really simple. So notice that this one is to find the solution or the root. So it's x sine of x plus 1 equals 0. So that's what you're doing. So you're looking for the root of that function, 0. So that's what you're doing. So you're looking for the root of that function here. It's another equation. And these are all equations. What I like about these that I don't like about 5b is that these are equations that I have no idea how to solve analytically. Isn't that great? So these are equations that we have no, like, how are you supposed to solve this? And your sine of x minus x squared. So all you have to do is you have to do, let's see, it says, oh, M4. So you're doing 4 rounds of this bisection method. M3, 3, so it's simple. Okay, so here's where things get tricky. It says, I want to have an absolute error of no more than 1/4. So I wanted to make sure I mentioned this, and I also want to mention something about those over there, and then we'll be done. We can go start our game time a little early, possibly. So here, where's the iPad? There it is. Okay, so when it says that it wants us to have an error of less than 1/4, let's just suppose that I was going to do this problem with an error of less than 1/4. Well, what you could do is you could do here, you could do max. Here, how close? I like that better than max error. Technically, that how close up there is, yeah, maybe I should make how close. It's really the maximum error. What's the worst? If you say this is the answer, but you know the answer is somewhere between 0 and 1, the worst case scenario is that you're off by 1/2. So that's what it's referring to, is that. So if I was told to do this problem until I was within 1/4 of the truth, then I would just keep going. Let's see, this is going to be, let's see, I guess the maximum error is 0.6. Wait a minute. How far? Oh, yeah, I just realized I have to add, okay, it's 2.5 minus, I added them together, get the midpoint, but to find the maximum error, oh, it'd be 2.5 minus the midpoint. That would do it, 0.625. It's 1.875. So I just took the difference between these two, because presumably that's in the middle. And so the worst case scenario is that you say this is the answer. The true answer is either down here or up here. So that's how close. So I would keep going. The next one would be, let's see, subtract 2.5 and 1.5625, and you get 0.9375. The next one, you would subtract this and this to get how far you are from the truth, and you would get 0.46875. You might wonder, how did I do that without knowing what that is? Well, does anyone know how I figured out what the maximum error was? What do you notice about those maximum errors? It was really obvious on the other one. What do you think? Yeah, it's half the one above it, because you're splitting the interval. So now we're going to make even half the size, then half the size. So the next one's going to be half of this. So if we wanted to be within 1/4 of the truth, we would want to go down here, because the next one, the very next one down, is going to be with numbers 15 and 16, because they seem a little bit open-ended, but they aren't. Find a lower bound on the number of iterations that it would take to guarantee an accuracy of 10 to the negative 20th. So I want to be within 10 to the negative 20th of the truth in whatever problem that I'm working on. So let me just show you how I would do this with this problem. So here, let's get rid of this. So here's how I might do this. The error is equal to 1.875 times 1/2 to the nth power. Kind of makes sense that you started with an error of 1.875. I guess technically it would be the whole interval times 1/2 to the nth power. It's fine. But yeah, so technically I think that you would want to start with the entire interval, but which would be twice this. Doesn't matter. But anyway, so this is half of 1.875. That's another half, which is 1/2 squared, and so on. So we've got a nice formula now that we know the size of the interval. And I want that to be less than 10 to the negative 20th. So for this particular problem, I just have to solve that. That's not a bad equation to solve, is it? Let's try. We have 1/2 is less than 10 to the negative 20th over 1.875. Oh, sorry, 1/2 to the n. I don't like the fractions the way they are. And so I'm going to flip this thing over, 2 to the n. And since I just reciprocated, I have to do it this way, 1.875 times 10 to the 20th. There, that looks a lot better to me. So I just reciprocated both of these, and when you do reciprocals, it's like multiplying by -1. You have to change the direction of the little alligator. It always points towards the bigger number. Yeah, if this is smaller than this, then when you reciprocate, that will be bigger. Another way of looking at it. Almost done. Now n should be greater than the log base 2. Sorry, that's supposed to be a 2 of 1.875 times 10 to the 20th. And there it is. So let's find this out on the calculator. I don't know, does your calculator do log base 2? I know how to fool it into doing a log base 2, but I don't know if it has a log base. I have a log button, but that's the log base 10. Let me look at the catalog just for fun, and then I'll give up. I'll just show you. Maybe I'll just show you just a sec. I'll show you the way to do it. Here. So you want to do the log base 2? Here, let's see. Can I get split view? Oh, really? There's a math A? Math A? I don't have math A. Mine ends at 0. Wait, is it over here? Okay, well, you might have a log base 2. If you don't, here's how you get it. You do the, give me a sec here. I can't see my problem. Okay, here, I'll write it down. So that is equal to the natural log of 1.875 times 10 to the 20th divided by the natural log of 2. That's the way you would not cheat, the way you would get a calculator that doesn't have a log base 2 to do a log base 2. So let's do this log of 1.875 times 10 to the 20th divided by the natural log of 2, done. 67. N is greater than 67.3. All right. Oh, yeah. So in other words, 64. I mean, if it has to be bigger than 67.3, so 64. I'd have to do 64 iterations. Seems like a lot by hand, but a computer almost takes no time at all. So not too bad. So you'll have questions like that. So are there other concerns? You think you got this now that we've gone over it in class? Aren't the remote days terrible? I could have been here, no problem. Although I got to be honest, I was thankful. I was dealing with some additional issues, both issues related to my job, as well as some personal issues that I had to take care of, which it was nice to have a day to do those after getting up at 4 to shoot a bunch of videos. All right, well, yeah, we're done a few minutes early, so you can get extra hot dog from the cafeteria, or we can get started on playing this game a little bit earlier. Yeah, I'll stop the recording though, just in case someone wants to listen.